Okay, so if you continue the discussion from the last part, we can say that there are uh, total number of charge that is moving through this element dl, which constitute the current I. If we denote it by the number dq, then dq will be equal to, I have already calculated, and its value is n a dl into small q. Okay, this value we have already calculated. Okay, so now what we have to determine, we have to determine the value of the magnetic field at the point P, which is at a distance r. Suppose this is the origin O, then at a distance r from the point O. Okay, and the direction of this position, the direction of the point P is denoted by this position vector r cap. Okay, so what we can say that the magnetic field due to each of the charge that is flowing through this element is equivalent to the total magnetic field produced by one single charge dq that is traveling with a velocity vt. Okay, this is due to the consequences of the superposition principle. This is a very important theorem. Let me remind you it again. Okay, we know that there are n a dl q number of charge flowing through that element, and each of that charge will produce a individual magnetic field. Okay, and we have to sum up all those magnetic field to get the value of the total magnetic field. Okay, and this magnetic field will be equivalent to, if we imagine there is a charge dq which is flowing through that current element dl, because the velocity of this charge dq is equal to velocity of each individual charge that is passing through the element. Okay, so now what we have to determine, we have to just determine the magnetic field at the point due to this charge dq, and then it will automatically taken into account all the charges that is moving through the current element. Okay, so if you remember the last lecture, then what is the value of the magnetic field at the point P? Let denote this magnetic field as dB, because we are denoting the charge as dq. Okay, so what is the value of magnetic field due to this charge dq at the point P? dB will be equal to, if you remember the last lecture, the value magnitude. I am not bothering about the direction. Direction we can always determine for all this kind of thing. We can determine from right hand thumb rule. Okay, now just concentrate on the magnitude of the field. That magnitude will be mu naught divided by 4 pi, that we know. Then we have to multiply the charge with the drift velocity, because each charge moving with a similar velocity. So value of each charge is q. Say I have taken it as the modulus, because if it is minus, then if we take the modulus, then it will give the positive quantity. Okay, so q into vd. Okay, and then we have to multiply it NaDl. Okay, NaDlQ, that is the total charge dq, and which we have to multiply with vt, the drift velocity, divided by r square. Okay, and then what is the angle between the radius vector and the current I, or here the length of the direction of the current element is taken in the same direction as the current is in the x direction, therefore dl will be also in the x direction. Okay, and with dl, what is the angle subtended by the position vector? This is phi. Therefore dB will be equal to mu naught divided by 4 pi q v vd NaDl divided by r square into sine phi. That is the value of the magnetic field at the point P due to this current element. Okay, now we can do one thing. Okay, so what we can do, we can express n q vd into a. This is equal to current I. Okay, this expression in current electricity, you are going to prove this expression. For the time being, just assume that I is equal to n q vd into a. Actually, this factor we have to look. We have to see whether this expression is dimensionally equivalent or not. Okay. For that, let's do the dimensionless analysis. We know the small n donate the number of charges per unit volume. Therefore, its unit will be equal to meter to the power -3. Charge as the unit of coulomb, okay, and velocity meter per second, and area is equal to meter square. Okay, so what is give meter cube, sorry, 1 by meter cube into charge divided by second. Meter cube cancel out, charge divided by second, so it has the dimension of current. So automatically we can prove that this expression is right. Okay, so in the place of NQ VD into A, what we are going to replace? We are replacing this factor with this factor, which is the current I passing through the current element. Okay, so dP, what we can write, mu naught divided by 4 pi, put the I here, okay, I dl sine phi over r square. Okay, this is the expression for magnitude of the magnetic field at the point P. Okay, now we know that magnetic field is a vector quantity. Okay, so similar kind of treatment we'll do, which we have done in the previous part. So basically, you see, current is a scalar quantity. It doesn't have a direction, and magnetic field is a vector quantity. Okay, so to find out a vector quantity in the right hand side, we have to express this expression as a cross product between two vectors. Okay, so we'll take dl as a vector, and I have already told you that dl has the same direction as the current itself. Okay, so if we take it like that, then in the vector format we can write dB is equal to mu naught divided by 4 pi I, okay, dl cross r vector divided by r square, because r cap and dl vector, the angle between them is phi. Therefore dl cross r cap is nothing but dl modulus r cap modulus sine phi into n cap. Okay, and this value is equal to 1. Therefore dl sine phi into n cap. N cap is the here the direction of the magnetic field. Okay, so in vector notation, if the current element dl carrying a current I, then the magnetic field at a distance r from the center of that element is given by mu naught divided by 4 pi I dl cross r cap divided by r square. Okay, this is another statement of Biot-Savart law. Biot-Savart law. Okay, so if you have a current element dl and it is carrying a current I, then at a distance r from the center of the current element, the value of the magnetic field dB is equal to mu naught over 4 pi I dl cross r cap over r square. Okay, and the direction of this magnetic field, actually we can determine it from the right hand thumb rule. What do you have to do? You have to put your thumb in the direction of the current, and you have to curl your finger. Okay, this direction of the curl of the finger will give you the direction of the magnetic field. So since the curl is a closed cycle, because if you curl the finger, then it will produce a closed curve. Okay, so the direction of the magnetic field is closed one here. Okay, so for example, if you say this is the direction of the current, then the magnetic field will be like this. It will be a closed circle. It will be just like this. This is the magnetic field. Okay, here the current is flowing like this, and the magnetic lines of force or magnetic field will be a complete cycle across that current element. Okay, so if you remember, if this is the current element, then your magnetic field will be a closed circle across that current element. Okay, so using the right hand thumb rule, we can determine the magnetic direction of the magnetic field for such kind of cases, because here if I plot the direction, it will not visible to you. So it's basically it's better to remember the right hand thumb rule. You just put your thumb across the current and just curl your finger, okay? And pictorially, if this is the current is moving inward and through the current element, then the direction of the magnetic field will be like that. It will be a closed loop, okay? Magnetic lines of force are always closed, unlike the electric lines of force which are diverges from the point of origin, okay? So this thing you have to remember, this is the Biot-Savart law for a current element dl carrying a current I. Okay, so in the next part of the video, what I'm going to do, I'm going to determine the magnetic field due to a straight conducting wire. Suppose this is a straight conducting wire. We know the current element dl, what is the value of magnetic field. So basically what we have to do, we have to sum up all those ds elements to get out the, find out the magnetic field at a certain point P. So next class I am going to determine the magnetic field due to a current carrying conductor. First I have determined the magnetic field due to a Q charge Q. Then after that, when I add up all those Q, I got the magnetic field due to a current element dl. And when I add up all those current elements, then what I will get? I will get the magnetic field due to a current carrying conductor. Okay, so we have to go step by step. First Q, then dl, and after that we have to determine the magnetic field due to the whole current carrying conductor of length L. Here L is very greater than dl. So in literature it is termed, it will be, you will be heard most of the time people are talking about infinite length of wire. Infinite length of wire. Okay, because the current element here is much less, length of the current element is very less than the total length of the current conductor. That's why compared to the dl, it is of infinite length. Okay, so next part of the video will be magnetic field due to a infinite current carrying conductor, B due to infinite current carrying conductor. Okay, so see you in the next class. Okay.